Okay, we're going to do problem number 4 in section 2. So we have y is equal to the square root of 9 minus x squared, and we're rotating around the x-axis because that's what the problem statement says. The limits of integration, I'm going to let you look at the figures. So if you look at your figure, you'll see that both x and y vary between 0 and 3. But we're going to be integrating with respect to x. So the limits of integration for x are going to be x equals 0 as our lower limit, and x equals 3 as our upper limit. And the bottom of the area corresponds with the x-axis. So in that case, the volume of this curve rotated around the x-axis is equal to pi times the integral from a to b of r of x, which is the curve which defines the upper boundary, r of x quantity squared dx. So in this case, r of x is just equal to the square root of 9 minus x squared. And it's a function of x because x is on the right-hand side. So r of x is equal to y in this case. So now we can plug things in. So we get pi, the integral from 0 to 3. R of x is the square root of 9 minus x squared. We square that quantity and we multiply by dx. So we multiply out. So we get 9 minus x squared dx, because the square of a square root is just the quantity. So this is a simple polynomial integration. So we get pi, which is our constant, times the integral of 9 dx, and that's equal to 9x. We subtract off the integral of x squared dx, which is x cubed over 3. And we'll evaluate that integral between x equals 0 and x equals 3. So the upper limit is 3, so we take 9 times 3. We subtract 3 cubed divided by 3. So that's the upper limit. And we subtract the lower limit, which is going to be 0 minus 0, because we have zeros in those polynomials. So 9 times 3 is 27, and then we get 27 divided by 3. So you multiply 27 by 3, which is 81. So we'd have 81 thirds minus 27 thirds, which is equal to 54 thirds. And I don't think you can divide, well, maybe you can. Actually, you can. 54 divided by 3, use a calculator. 54 divided by 3, and make sure it gets right, 18. So that's going to be 18 pi. Okay, well, we're going to try to do this again. I did it once and got all the way to the end and realized I messed up something in my integration. So then I fixed it and I got the right answer. So at least I know where to keep an eye out. So this is problem number 6 on page 463. It was a homework assignment. So if you're diligent enough to be looking in here and you still had a problem getting this solution, then you will get it before it's due. So these are the two curves, and the curve is shown in the book, and we showed in the study session that we find the limits of integration by setting these equal to each other and solving for the values of x, where this equality goes to 0, and that's when the two curves intersect. So if we would subtract 4 from both sides, we would get negative 2 is equal to minus x squared over 4. If you multiply by negative 4, you get 8 is equal to x squared, and therefore x is equal to plus or minus the square root of 8, which is also plus or minus the square 2 times the square root of 2. So those are limits of integration, but because of symmetry, we can do half of the volume and then multiply it by 2, and that'll reduce the work by making it so that the limits, one of the limits is 0. So our equation for the volume of this area rotated around the x-axis is going to be 2 because we're doubling it, and we're only integrating from 0 to plus the square root of 2 times the square root of 2. It would also be the same as pi times the integral from negative 2 times the square root of 2 to positive 2 times the square root of 2. Now the curve that's on top is this one. So we take 4, so this would be big R of x. So let's just write this down. R of x is the outside radius, which is 4 minus x squared over 4. And our small radius is the inside radius, which would be 2. So we can just plug those in there. So this is big R of x squared minus little r of x squared. And now we just need to multiply these things out and see if we can combine some terms. So we just want to get a polynomial. So we'd have 2 pi. Actually, let's figure out what this term needs to be in here. So if we multiply this out, 4 minus x squared over 4 quantity squared, do it the 2 ways, the mental way and the longer way. So mentally, when you have a perfect square like this, you square the first term. You take this times that, which would be 4 times negative x squared over 4. The 4's cancel out, and so you just get negative x squared. And you have 2 of those because you have both the inner and the outer. And then you multiply this, you square this part, which would be plus x to the 4th over 16. So that's the result. You could also just write it out as a multiplication here and just go through the long way. So what you'd have is 16 first. Inner would be negative 4 times x squared over 4. So that was the inner. The outer would be negative 4 x squared over 4. And last would be positive, because negative times negative is positive, x over 2, x squared over 4 squared. So we get 16 minus, these cancel out, so you just get negative x squared, so that's 2, negative 2x squared, and then we get plus x to the 4th over 16. So that's so let's just plug those into the integral. So our volume again is equal to 2 pi times the integral from 0 to 2 times the square root of 2, and we'll have 16 minus 2x squared plus x to the 4th over 16, and then we subtract 4, which is 2 squared. So we can combine the 16 and the 4, so we get 2 pi, the integral from 0 to 2 times the square root of 2. So we have 12 minus 2x squared plus x to the 4th over 16, the whole thing times dx. And the last thing I'm going to do is I'm going to factor out 16th. And the reason I do that is just so I get whole numbers instead of fractions when I integrate. So the way this works is if you factored 16 out, you have to multiply by 16. And so we take 12 times 16, 192, minus 16 times 2 is 32, and 16 divided by 16 is 1. So these are equivalent. You can see if I divide by 16 I get that, divide by 16 I get that, and divide by 16 I get that. So now we're going to just do the integration. So we get 2 pi over 16, and the integral of 192 dx is 192x. Integral of 32x squared is 32x cubed over 3, and the integral of x to the 4th is x to the 5th over 5. And we evaluate that between x equals 0 and x equals 2 times the square root of 2. Now the advantage here is when I plug 0 in at the lower limit, these all go to 0. So all I have to do is evaluate the upper limit. So let's do that on a separate page. So we have 2 pi over 16, and we have 192 times 2 times the square root of 2 minus 32 times 2 times the square root of 2 cubed over 3 plus 2 times the square root of 2 to the 5th power over 5. This is where I messed up last time, as I forgot the 5. Now, we can factor out a square root of 2 times 2. So we'll have 2 times the square root of 2 times pi divided by 16. And what that leaves is it leaves 192 here. When you take 2 times the square root of 2 out of here, you end up with 2 times the square root of 2 squared. This is the square root of 8. So if you square the square root of 8, you just get 8. So I'll have 32 times 8 divided by 3. And here the same thing. When you take 2 times the square root of 2 out, you'll have 2 times the square root of 2 to the 4th power, which is the same as 8 to the square root of 8 to the 4th power, which is the same as 8 squared, which is the same as 64. So we have plus 64 fifths. Now we need to find a common denominator. Now let's go ahead and simplify this a little bit. 2, we can cancel out. That's 4. And you can cancel out a 4 there, so we'll end up with the square root of 2 times pi over 4. And to get the common denominator, we need to multiply this by 15. So we have 192 times 15 is 2,880 fifteenths minus. We need to multiply by 5 to get 15 in both the numerator and the denominator. So we take 32 times 8 times 5. That's equal to 1,280 divided by 15. And then we have 64 times 3. So we'll get 15 again in the denominator. So 192 divided by 15. So if you do all that, 2880 minus 1280 plus 192, you get 1792. So we get the square root of 2 times pi divided by 4 times 1792 divided by 15. And if you divide 1792 by 4, you get 448. So we get 448 times the square root of 2 pi divided by 15. So this part right here becomes 448, square root of 2, pi, and then we have 15. So that's it. That's the correct answer. This is problem number 7, section 2, chapter 7, section 2, number 7. And again, the graph is in your book, and so what we have is y is equal to x squared, which is a parabola that goes through x equals 0, y equals 0. Just a normal standard parabola. And you can see the area that they're asking us to rotate around the y-axis. So this is going to be a y-axis. what does that tell us? Well, it tells us two things. It tells us if we're using the disk method that we need to use this equation. The volume is equal to pi times the integral from c to d of r of y, quantity squared dy. So you can see from the equation that it's going to be a integration with respect to y. So our equation is y as a function of x. We need x as a function of y. So we have to take this equation and rewrite it. And since we're doing just the right-hand side of the equation, if we solve for x would be plus or minus the square root of y, but we're only going to use the positive square root because that is the part of the curve that's shown in the graph. The negative would be the left-hand side of the parabola. So this is r of y. That's the curve that defines the outside of the volume that's revolved around the y-axis. You can also look at the graph and you can see that the y value varies between 0 and 4 on the y-axis. The x variable varies between 0 and 2, but we're rotating around the y-axis, not about the x-axis. So all we have to do is just plug in now. The volume is equal to pi times the integral from y equals 0 to y equals 4 of r of y, which is the square root of y. And we square that and we multiply by dy. So we multiply out what's inside. Square root of y squared is y. And then we can integrate. The integral of y dy is y squared over 2. And we integrate that between y equals 0 and y equals 4. So we just evaluate this at the upper limit and subtract this evaluated at the lower limit. The lower limit is going to be 0 because 0 squared is 0. So the final answer will be pi times y at the upper limit, which is 4 squared divided by 2. And I'll put the 0 in there. 0 squared is 0. So we get 16 over 2, which is 8. So the answer is 8 pi. This is problem number 9, section 7.2. So just like problem number 7, we're going to integrate with respect to y rather than x because we're rotating around the y-axis. So our volume for using the disk method is pi times the integral from c to d of r of y, quantity squared, dy. So just like before, we need to rewrite this equation as a function of y instead of a function of x. So if you think about this, we take y equals x to the 2/3, and what we want to do is we want to get x to the first power, which is what we're solving for. So we have to take it to the 3/2 power, because then we would multiply the exponents together and you'd end up with 1. So since we are raising that to the 3/2 power, we have to do the same thing here. So the conversion then becomes x equals y to the 3/2 instead of y equals x to the 2/3. So these are equivalent expressions. And if we plotted this, we would get the same thing we have in the book. Now our y limits of integration here on page 463 are the same as the x limits in this case, which are from y equals 0. So our limits are c is equal to 0 and d is equal to 1. So therefore the volume is equal to pi times the integral from 0 to 1 of the quantity r of x, which is y to the 3/2, square the whole thing times dy. So when you square this, we multiply 3/2 times 3/2, and actually that's not true. We multiply 3/2 times 2. So we're going to get pi times the integral from 0 to 1 of y to the 3rd power dy. So 3/2 times 2 is 3. And if we integrate that, we get pi times the quantity y to the 4th over 4 evaluated between 0 and 1. Evaluating at the upper limit, which is 1, we get 1 to the 4th over 4, and subtracting at the lower limit, we get 0 to the 4th, of course, which is 0. And so the final answer is going to be equal to, the volume is going to be equal to pi over 4. And that is the correct answer. This is problem number 12, which is a fairly long problem, but it covers a lot of information, so hopefully you'll bear through this. We have the same area, but we're going to rotate it about 4 different axes. So these are our restraints on the area. So again, I'm not sure what this looks like, so we're going to plot it and then bring it into the notebook. So we just want to plot the function, which is 2, well, we sort of know, well, it's a parabola, so we would have 2x times x. That would work, 2x squared. We graph it, and there's our parabola. And let's just zoom in a little bit in the x direction. And actually want to make sure we include all the limits that we need. We need an line x equals 2 and a line x equals 8, y equals 8. Okay, that should be good. And I'm going to get my camera. So let's take a picture of this. And let's go back to the Smart Notebook now. So what I'm going to do is I'm going to set each one of these up first, and then we'll look at them individually. So I'm going to create 4 copies of this page. So let me just clone this page 4 times, and then we'll look at each one of the 4 cases separately. So let's add a page and put both of them up here. So the first one says that we do the y-axis. So this is going to be a vertical axis of rotation. I should have put in these other things before. So we got y equals 0, which is this line, and we've got x equals 2, which is this line. So we only need 3 sides to define this area. And so the first case is we're going to rotate around the y-axis. So our limits of integration, this is 8, this is 0, and our representative rectangle is going to look like this, because we're using the disk, we're actually using the washer method here. So we have an inside radius and we have an outside radius. So this is one where we use the washer method. And let's just write the equation down. So the volume for vertical axis of revolution for the washer method is the integral, pi times the integral from C to D of R of y squared, that's the outside radius, minus small r of y squared, the whole thing times dy. We're integrating with respect to y, so in this case our limits of integration are going to be y equals 0 to y equals 8. Okay, so the rectangle moves up and down. So what's capital R of y? Well, in that case, it's x. It's going to be a function of x, and it's x equals 2 because this is 2 right here. So it's just going to be 2. X equals 2. And small r of y, which is the inside radius. So let's draw those radiuses on here so we get this straight. So this is small r sub y, and this is r of y. And this is big R of y because the area is in here. So this is capital R of y, and this is little r of y. Now we have to rewrite the original function as a function of y. So let's do that down here. So we get y over 2 is equal to x squared. Therefore x is equal to the square root of y over 2. And it's going to be plus or minus, but we're going to use just the plus side is this side, the minus side is that side. So we just want the plus side. So we can do the square root of y divided by the square root of 2. Yeah, we don't need to, because we're going to square it, so it'll all work out. So we get the square root of y, square root of y over 2. Okay, so that's our outside radius, that's our inside radius. So let's plug into the equation the appropriate stuff. Pi times the integral from 0 to 8 of capital R sub y, which is 2 squared, minus little r sub y, which is the square root of y squared over 2 squared, the whole thing times dy. So let's multiply it out and see what we get. So we'll have 4 minus, here we're not squaring the negative sign. We're squaring the square root of y squared over 2. So it's going to be y over 2 times dy. So now we can integrate. So we'll have pi. The integral of 4 dy is just 4y. The integral of y over 2 dy is going to be y squared over 2 divided by 2, which is y squared over 4. And we evaluate that between 0 and 8. We just evaluated the upper limit because it's polynomial, and the lower limit is 0. So we have 4 times 8 minus 8 squared over 4. Pi times 32. 64 divided by 4 is 16. So we'll have 16 pi. So that's part A. That's about the y-axis. Okay, let's go to part B here. Part B says to rotate it around the x-axis. So we're going to rotate, let's draw the area again. So y equals 0, x equals 2. So again, it's this area. We're going to put a rectangle. We're using the disk method, so the disk is like this. We're rotating around the x-axis. This is a horizontal axis. So what are our limits of integration? Well, we go from x equals 0 to x equals 2. So that's our limits of integration. The volume of a surface of revolution around a horizontal axis is the integral from A to B. In this case, it's just a disk because we go right to the x-axis. Okay, the bottom of the rectangle is the x-axis. So we just have to do r of x, quantity squared, times dx. And we can just use this curve directly because it's a function of x. Pi times the integral from x equals 0 to x equals 2 of 2x squared quantity squared dx. That's because r of x is just equal to 2x squared. We multiply it out, and we get 4x to the 4th dx. So I'm going to factor out the 4, so we'll get 4 pi. The integral of x to the 4th is x to the 5th over 5. And we'll evaluate that between x equals 0 and x equals 2. So we have 4 pi times 2 to the 5th over 5 minus 0 to the 5th over 5. And 2 to the 5th, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we'll have 4 times pi times 32 divided by 5. And 4 times 32 is 128. So we'll have 128 pi divided by 5. And that's the correct answer. So that's part B. Part C. Part C, it says we want to rotate around the line y equals 8. So again, let's draw our limits in here. Y equals 0, x equals 2. We're going to rotate around y equals 8. So this is y equals 8. And this is the area we're talking about. So let's put a, since it's a horizontal axis of rotation, we're going to draw our rectangle vertically because we're using the washer method in this case. And the radiuses are from the line y equals 8. So we'll have the inside radius will be to the function, the other side of the function, and the outside radius will be to the x-axis. So this is r of x, and this one will be small r of x. So using the washer method, it says the volume for a horizontal axis of rotation is pi times the integral from a to b of the outside radius squared minus the inside radius squared times dx. We're integrating with respect to x. And so our limits of integration are going to be from 0 to 2. So a equals 0, b equals 2. R of x, the outside radius. Well, the outside radius is this. It's a constant. It's equal to 8. I almost said 4, but it's really 8. Small r of x is also going to be 8. The total distance subtracted this distance, which is the value of the function. So we'll have negative 2x squared. Total distance is 8. This distance is 2x squared, so this remaining distance is 8 minus 2x squared. So now we're plugging in. The volume is equal to pi times the integral from 0 to 2 of 8 squared minus 8 minus 2x squared times dx. That's because this is 8, so we square 8. R of x is this, so we square the whole thing. We multiply the terms out. So 8 squared will be 64. Here we get 8 squared, so let's put a minus sign here for this minus sign. So we'll end up with 8 squared, which is 64. 8 times negative 2 is negative 16, and we double that, so we get negative 32x squared. And then we square this term. Negative 2x squared is going to be positive 4x to the fourth. And that whole thing is times dx. Okay, one last step before we integrate is we integrate from 0 to 2, x equals 0 to x equals 2. These cancel out, and we have a negative times a negative, so we'll have 32x squared minus 4x to the fourth, the whole thing times dx. The negative sign comes from here. Negative 1 times 4. 4 is negative 4. Okay, so let's bring that down. So now we integrate. So we have pi times 32. The integral of x squared is x cubed over 3. The integral of x to the fourth is x to the fifth over 5. And we evaluate the integral from x equals 0 to x equals 2. So plugging that in, we get 32 times 2 cubed over 3 minus 4 times 2 to the fifth over 5. So let's just multiply all this stuff out. So 2 cubed is 8. So 32 times 8 is 256. So we have 256 over 3 minus 2 to the fifth is 32. So we have 32 times 4, which is 128. And we find the common denominator 15. So we're going to multiply this by 5 in the numerator and the denominator, and this one by 3. So 256 times 5 is 1280, and it's over 15. And then we take 128 times 3, 128 times 3, that's 384 divided by 15. And so 1280 divided or subtract 384, we get 896. So we get 896 pi over 15. And it's definitely not going to be divided by 5, so let's try 896 and divide by 3 and see if we get a, no. So that's as much as we can reduce it. And that is the answer, correct answer again. So 3 for 3 so far. Okay, the final one is this one. And for this one, it says we want to integrate around the line x equals 2. So again, defining our lines, we had y equals 0. We had x equals 2. And we're rotating around x equals 2. So we're going to rotate around this axis, which is a vertical axis. So the vertical axis says that for the disk method, and our disk is going to look like this. Our rectangle is going to be aligned like this, and you'll rotate it around the x equals 2 axis. So it'll be a disk without a hole in the middle. So it is going to be a disk and not a washer. Okay, so we're rotating it around x equals 2. So anyway, for a vertical axis of rotation, the disk method says that the volume equals pi times the integral, and we're going to be integrating with respect to y. See how the way the rectangle is oriented. So we're going to go from C to D, and we'll do r of y, quantity squared dy. So what is the radius in this case? Well, it's the distance from the axis of rotation to here. Now this total distance is 2. And so if we do r of y from here to here, which is what the function will tell us, then we take 2 and subtract off that, and we end up with that left. So we already did that before. What did we find out? We found out that if we write it as a function of y, r of y, let's not r of y, but let's solve the equation for y. So we had y squared is equal to 2x squared, and therefore x was equal to the square root of y over 2. So that was our function. But we don't use that. We say that r of y is 2, this total distance, subtracted off this y over 2. Okay, so that's r of y. Our limits of integration are from y equals 0 to y equals 8. So our volume is equal to pi times the integral from 0 to 8 of 2 minus the square root y over 2 quantity squared dy. So let's do it. First, we got to multiply it out first. Pi times the integral from 0 to 8. So what do? We get 4. 2 squared is 4. Then we have 2 times this, and then we double it. So we're going to have negative 4 times the square root of y over 2. And then we square this. If we square that, we get plus y over 2. Whole thing times dy. And now we integrate. 4 dy, the integral of 4 dy is 4y. Here what we have is, let's rewrite this as 2 separate terms. So it's the square root of y. So we'll have 4 divided by the square root of 2. That's what we get from these two parts. And then we integrate the square root of y, which is going to be y to the 3 halves divided by 3 halves. And I think that's right. Yes, because if you take the derivative, you'd get 3 halves times divided by 3 halves would give you 1, and you get y to the 1 half. And then here we have y squared over 2 divided by 2 again, so we get y squared over 4. And we evaluate that between 0 and 8. So let's plug the numbers in. Just have to plug the upper limit in. So we get 4 times 8 minus 4 divided by the square root of 2 times, I'm going to, instead of dividing by 3 halves, I'm going to multiply by 2/3 times 8 to the 3 halves plus 8 squared over 4 minus 0 for the lower limit. So we have 32. So 8, if you take the, if you take 8, so what do we get here? Let's think about this. Let's go down here to do this 8 to the 3 halves. How do we do that? Well, you could say it's the square root of 8. So this is the same as the square root of 8 cubed. And the square root of 8 is 2 times the square root of 2 cubed. So 2 cubed is 8. And the square root of 2 cubed is going to be 2 times the square root of 2, which is going to be equal to 16 times the square root of 2. So let's plug that in here. Minus 4 over the square root of 2 times 2 divided by 3 times 16 times the square root of 2 plus, okay, what we have here is we have 64 divided by 4, which is 16. So let's see if we can simplify this thing here. These cancel out. And then we'd have 8 times 16, 8 times 16, 8 times 16 is 128. So we'd have 32, let's go ahead and, 32 minus 16 is 16. So I'm taking this, actually it's plus, it's not minus, plus. So 32 plus, that's 48. And we subtract off 128 divided by 3. So if we multiply this by 3, 48 times 3 is 144. 128 divided by 3. So 144 minus 128 is 16. So we get 16 pi over 3, which, lo and behold, is the correct answer. So there we go. So you can review this video all the way through if you want to see it again. It is long, but it does cover a lot of bases. If you understand this, you're in good shape. Okay, we're going to do problem number 16, section 7.2. So it says we have a curve y equals 1/2 x cubed, and we have another straight line of y equals 4, not y equals 0, let's fix that. Y equals 4 and x equals 0, and it says we're going to rotate around the line y equals 4. So let's not draw anything, let's use our graphing program. So I'm going to switch over to that. Okay, so there's something from a previous problem, but the function we have is 0.5 or 1/2 times 0.5 times x cubed. So let's graph it. And it says we're going to have a line y equals 4 and a line x equals 0. Okay, so this should work as far as the dimensions are concerned. And I'll be back in just a second. I'm going to get a picture here. Oh, wrong button, sorry. Okay, let's try it again. Okay, bear with me here. I've accidentally done something I shouldn't do, but everything will be fine. Okay, so I want to take a picture of this graph, and I'm going to go back to the back to the Smartboard file. So here we are. So there's the graph, and that's just of y equals 1/2 x cubed. So let's draw these other lines. And so we have a line y equals 4, so let's draw that horizontal line, and a line x equals 0. So what we can see is it's this area right in here that we're going to find the volume associated with that, and we're going to rotate around a line y equals 4. So this is y equals 4, and so this will be our axis. This will be our rotation. It's a horizontal axis, but it's not equal to the x-axis. Okay, let's go ahead and put in a little rectangle to represent what we're doing here. So we're going to integrate with respect to x, and so we're just going to have these rectangles that we're rotating around, creating disks, and then we're going to stack those all up through here. So it'll be basically a point here, kind of a dull point, and then this will be a flat area. Okay. So let's add another page. So this is still the disk method. It's just that the inside radius or the outside radius is going to be shown as such. So you go from the axis of rotation down to the function. So this will be the outside of the rotated element. The inside is just the same, corresponds with the upper boundary of this area corresponds with the axis of revolution, so we don't have to do anything there. So for a horizontal axis of rotation, what you have is the volume is equal to pi times the integral from a to b of r of x quantity squared times dx. The limits of integration from a to b are going to be what are the limits in the x direction. So we start out here at x equals 0 and we go to x equals 4. So that's going to be our limits of integration. X equals 0 to x equals 4, actually it's equal to 2. Y goes to 4, but x goes to 2. Now the radius around this line y equals 6 is going to be the total distance from here to the x-axis, which is 4, subtracting off this function, which is the distance from the x-axis, and that will give us the remaining distance. So in this case, r of x is equal to 4, which is this, minus the function, which is 1/2 x cubed. So that's r of x. So now we just plug in. The volume is equal to pi times the integral from 0 to 2 of the quantity 4 minus 1/2 x cubed squared. I probably put an extra parentheses that I didn't really need there. Okay, now we multiply out. So the volume equals pi times the integral 0 to 2, and we'll end up with 16, 4 squared. Then you take 4 times this term, which would be negative 2x cubed times 2, which would be negative 4x cubed. And then we do the last, which is this squared, which is plus 1/2 squared is 1/4, and then we have x to the 6th. The whole thing times dx. So 4 squared is 16. 4 times negative 1/2 x cubed is negative 2x cubed. We multiply it by 2 for the inner and the outer. We get negative 4x cubed. And then we square this. The negatives cancel out. We get 1/4 x to the 6th. Now we integrate. Nice simple polynomial integration. So we get 16x minus 4 x to the 4th over 4 plus 1/4 x to the 7th over 7. And that's integrated between x equals 0 and x equals 2. And now we plug in the numbers. Again, the lower limit is going to be 0 because everything's 0 in a polynomial comes out to be 0. So we get 16 pi times 16 times 2. The 4's cancel out here, so we don't have to carry those along. So we'll just get minus 2 to the 4th power plus 1/4 2 to the 7th power over 7. So we have 32. 2 to the 4th is going to be 2 times 2, which is 4, times 2 is 8, which is 16. And 2 to the 7th power, you get 2, 4, 8, 16, 32, 64, 128. So we have 128 divided by 7. And I forgot a 4 there too. Okay, so we got 128 divided by 4 divided by 7. So let's simplify a little bit here before we try to find a common denominator. So we'll have 16 minus 128 over 28. Let's go ahead and divide 128 by 4. 128 divided by 4 is 32. So we'll have 32 sevenths. And this should be plus. Okay, so we have to find a common denominator of 7. So we'll take 16 times 7. 16 times 7 is 112. So we have 112 sevenths plus 32 sevenths. And so that's going to be 144 sevenths. So we get 144 pi divided by 7. And that was problem number 16. So I'm just going to check it quickly here. 144 over 7. 440 pi over 7. So that's correct. Okay, what we're going to do is get another example of how you rotate around some line other than the x-axis. We're going to do it in the y direction this time. So the problem we're going to do is problem number 22 on page 463. So I think we're set now. Okay, so again, this is problem 22, and the equations are x, y equals 6, y equals 2, y equals 6, and x equals 6. And it says we want to rotate it around a line x equals 6. So actually I'm going to change this. I'm going to right? Yeah, I think I'm going to change that to 4, just to make it a little more complicated. So this defines the area that we're looking at. And as far as the function is concerned, as far as the, we're going to do it about rotate around a line x equals 6. So the first thing we need to do is we need to plot this and then bring the graph in so we can look at it. So let's go to the graphing program. So the functions are, and what I'm going to do is I'm just going to plot one of the functions, and it was x, y times x, x times y is 6. That's the same as y is equal to 6 over x. So let's put 6 divided by x in our graphing program. And we want to make sure we go at least out to x equals 6. So let's put it out to 8. And let's start at x equals -2. And we'll graph it and see what it looks like. Okay, so what we're going to do is I'm going to zoom out just a little bit in the y direction. Okay, so let us capture that. And you're going to see the screen go blank here for just a second while I get my camera so that I can. Okay, so we're going to highlight this picture. Hopefully it'll show up in the right place. Okay, we'll go back to the Smart Notebook now. Okay, there's our graph. And I'm going to move it down, squeeze it up a little bit, and do that. Okay, so let's go ahead and draw on here what we have. So the red curve is xy equals 6, and it says y equals 2. So let's draw a horizontal line at y equals 2. So that's this. And it says we want to draw a horizontal line at y equals 6 and x equals 4. So 1, 2, 3, 4. I don't know why it has the x equals 4 in there. Let me just look here. Actually, it says x equals 6. Because x equals 6 would be 1, 2, 3, 4, 5, 6. And that would be this line. So it seems like we're going to have two areas. Oh, actually, I see what it is. They want to do this one here. So it's actually right there. So that's x equals 4. This is y equals 2. So it's going to be this area, if that was the original one, but I changed it to x equals 4. So we're actually going to move it right here. Okay, so let's confirm that this is correct. And we're going to rotate it around a line at x equals 6. So this, whoops, sorry about that. Push the wrong button. So I'll put a vertical line here at x equals 6. So this is what we're going to rotate around the vertical axis, but it's not going to be equal to the y-axis. And so let's move up again, and see what we got. Okay, so this is y over xy is equal to 6, or y is equal to 6 over x. So that's that curve. Y equals 2 is this curve. Y equals 6 is that curve. X equals 4 is that curve. So we're going to rotate this around this. It'll be like a donut. This will be the outside of the donut. This will be the hole. And again, this is x equals 6 right now. So let's just draw some radiuses from the axis of rotation. So we would have an inside radius here, and we would have an outside radius. So this is going to be small r of x, the shortest distance from the axis of rotation. And this would be capital R, and actually it's going to be as a function of y because we're integrating the other direction. So let's fix that. Okay, so that's r sub y. And the limits of integration are going to be from y equals 2 to y equals 6. So let me put another screen up. And if you look in the book or in the notes, you see the volume of revolution when you're integrating with respect to y. And let me just put in, before we do that, let me put a rectangle in here. This is going to be more important when we start dealing with the next chapter, but you kind of put a representative rectangle in, which is going to be like this. And that'll create a washer if we rotate around this x equals 6 axis. Okay, so it's going to be the washer method. And in the y direction, it's the integral from c to d, and I forgot to put pi in there. I have a hard time remembering that. And so what you have is you have r of y squared minus small r of y squared, the whole thing times dy. In this case, c is equal to 2, because that's our lower limit of integration, and our upper limit of integration is going to be 6. We go from y equals 2 to y equals 6. Okay, now as far as these functions are concerned, r of y, this, and we have to solve it in terms of y, x is a function of y. So we start with xy is equal to 6, therefore x is equal to 6 over y when you use these as your limits of integration. So we can say that r of, well, actually that's not r of y yet, that's this distance. So this distance here is you take the total distance, which is 6, and you subtract off that distance, which is there. So r of y is going to be 6 minus 6 over y. Likewise, the small r of y is going to be the total distance from the y-axis, which is 6, and you subtract off the distance from here, the axis of rotation, to this curve, which is just a straight line, and that's at x equals 4. So we're going to subtract this distance is 6, this is 4, so this is going to be 2. So we're going to subtract 4 off, and so the inner radius is always going to be 2. This distance, you can see, no matter where we are, it's still 2 from as we integrate. Okay, once you establish that, the rest of it is just algebra and a little bit of calculus. So we have the volume is equal to pi times the integral from 2 to 6 of the quantity 6 minus 6 over y quantity squared minus 2 quantity squared, the whole thing times dy. So that's our integral. And what we're going to do, let's put this on one screen now, that we don't need the figure anymore. So you've got to multiply this stuff out. Let's get pi integral from 2 to 6. And if we multiply this out, you'll get 36, okay? Then you take 6 times this term, which would be negative 36 over y, and you double that, so you'll get negative 72 over y from the inner and the outer parts. And then we'll multiply this by itself, which will be plus 36 over y squared. And then we're going to subtract off 4. 2 squared is 4 dy. And before we integrate, we'll combine like terms. So 36 minus 4 is 32. So I have 32 minus 72 over y plus 36 over y squared, the whole thing times dy. Okay, I'm going to put 2 screens up here so we can look at it as we go along. Okay, now we integrate. So the volume is equal to pi. We integrate each term separately, so we get 32y. And if you integrate this will be the natural log. So we'll have negative 72 times the natural log of y. And here we'll have y to the minus 2. So let me just do this separately, this bit right here. So if you integrate that, 36 over y squared dy, that's the same as 36 times the integral of y to the minus 2 dy. So I've taken 36 out of the integral sign, and then I've changed this from a positive 2 in the denominator to a negative 2 in the numerator. So when you integrate that, you'll get 36, and you add 1 to the exponent, so you get y to the minus 1 divided by minus 1, and so you get negative 36 times y to the minus 1, which is the same as dividing by y. So this part becomes minus 36 over y. And we evaluate that between, we're integrating with respect to y, so we'll go from y equals 2 to y equals 6. So we just plug the numbers in now. So let me go back to one screen now that I have that over there. It gives me a little more room. So the volume, pi times 32. Now, there's another way you can do this. It might be a little easier. We can do each term separately and apply the limits. So we can have 32 times 6 minus 2. We can have minus 72 times the natural log of 6 minus the natural log of 2. And we can have negative 36 times 1 over 6 minus 1 over 2. We could have done each one of these, put 6 in and then subtracted the whole thing with 2. So in this case, because we have this natural log involved, we're probably not going to have, we probably end up with a decimal version anyway, so why don't we just go ahead and do that. So 32 times 4, which is 6 minus 2, is 128. We subtract off, let's see, natural log of 6. You can make sure you do these separately. It's not the natural log of the quantity 6 minus 2, it's the natural log of 6 minus the natural log of 2. which is 1.0986, and you multiply by 72, and so we get negative 79.1. And then finally we get 1/6 minus 1/2, should be 1/3, negative 1/3. So negative 1/3 times negative 36 is positive 12. So our final answer, we'll keep it in terms of pi, 128 minus 79.1 plus 12. So we get 60.9 pi is the volume of that rotated element. And since I changed the problem, I'm pretty sure I did it correctly, but I changed the radius so that we would get both an inner and outer radius. So let's go back and review this. This was the statement of the curves. And you got to use a little bit of thinking here. If you remember correctly, I thought it wrong initially, but the red curve is y equals 6 over x. It's a reciprocal function. If you plot a line y equals 2, it's a horizontal line here, and I plotted a horizontal line y equals 6. And when I did that, I originally thought of this area, but because I had this x equals 4 in there, that didn't make any sense. So I thought, oh, that's when I realized, oh, it's actually on the other side. So I ended up with this as my area. I'm integrating with respect to y, and I'm using the washer method. So I drew these two vectors, two arrows, to show that this would be the outside radius of the revolution, surface of revolution. This would be the inside radius, which is constant. R of y is going to be this distance, which is defined by the red curve, which is going to be equal to the red curve in terms of x as a function of y as a function of x is x is 6 over y. So I take the total distance, which is 6, and I subtract this distance, which leaves me that distance. So that's where I get big R of y, which is the outside diameter of this rotating thing. The inside is a constant with respect to y, and it's just equal to the total distance, which is 6, minus the distance from here to here, which is 4, and that's going to be 2. Okay, so those are the functions. The equation says you square this minus the square of that, and then integrate with respect to y. These are y limits of integration. So we go from the boundary here of y equals 2 to y equals 6. And we just plug it in, square that, clean it up a little bit, combine these two terms into a single term. Then we integrate. And so integrating 32y gives us 32, dy gives us 32y. The integral of negative 72 divided by y is negative 72 times the natural log of y. And here we showed the extra steps, but you end up integrating this term. 36 over y squared dy is negative 36 over y. And then we evaluated it at the upper and lower limits. In this case, I did it term by term. So you get 32 times the quantity y at the upper limit minus y at the lower limit, 6 minus 4, minus 72 times the natural log of 6 minus the natural log of 2, minus 36 times 1 over y. So we have 1 over 6 minus 1 over 2. And if you plug the numbers in, you get the result. Problem 23, section 2, chapter 7. So it says, find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis, which is a horizontal axis. So we have this function, and then we have y equals 0, x equals 0, x equals 3. So since they're not giving us the curve, we're going to look at it. So just bear with me here. I'm just trying to clean things up before I show you this next graph. So we'll go to the graphing program. So the function we're going to enter is 1 over the square root, 1 divided by the square root of x plus 1. So we're going to take a picture here of that and put it into our thingy-diggy. Make sure we got the limits right. Far enough along. Yep, we're okay. So let's go back to Smart Notebook. So that is 1 over the square root of x plus 1. So let's see what the other parts of the definition look like. So we have y equals 0, which is this horizontal line. We have x equals 0, which is this vertical line. And we have x equals 3. So you can see we've got a region bounded by those 4 curves. So this is the upper curve, this is the left-hand limit, this is the right-hand limit, this is the lower curve. So let's put a rectangle, a representative rectangle. We're going to do the disk method, so it's going to look, that rectangle is going to be rotated around the x-axis, which is going to create a disk. So let's put up a new screen so we can start putting some equations down. So the volume of a solid rotated around the x-axis is pi times the integral from a to b of r of x, which is the curve that defines the outer surface, squared times x. So our limits of integration are going to be from 0 to 3. So a is going to be equal to 0, b is going to be equal to 3. What is r of x? Well, that's this curve, and it's already a function of x, so that's good for me. So r of x is just 1 over the square root of x plus 1. So now we just plug in. So we have pi, the integral from x equals 0 to x equals 3 of the quantity 1 over the square root of x plus 1 quantity squared dx. So we multiply out. So we'll just get 1 over x plus 1, the whole thing times dx. So 1 squared is 1, and the square root of x plus 1 squared is just x plus 1. So what is the integral? Well, we're going to end up in a natural log. And if you let u equal x plus 1, we'll have 1 over u. And du will be just dx, so we don't really have to do anything here. So we can probably just write it out here as the natural log of x plus 1. And since x is positive, we don't have to worry about the absolute value sign, so we can take that off of there. And we evaluate that between x equals 0 and x equals 3. Now in this case, because it's not a polynomial, the lower limit is not going to give us 0. It's going to give us something other than 0. Possibly. Well, it actually does give us 0, but it doesn't necessarily have to be that way. So don't always assume it's 0. So you get pi times the natural log of 3 plus 1 minus the natural log of 0 plus 1. And the natural log of 1 is 0, so that is going to still go to 0. So we'll have pi times the natural log of 4. And let's just check. Yes, pi times the natural log of 4. And if you want to multiply that out, just to get a decimal, you'd have pi, oops, to turn my calculator on, pi times the natural log of 4. So it's 4.336. So that's the volume of this curve. Let's go back to the original picture of this thing rotated around the x-axis. Problem 33. So problem 33, you can find it in the book. Problem 33 says, find the volume of the solid generated by revolving the region bounded by the graph of the equations around the x-axis. Verify your results using the integration capabilities of graphing utility. Okay, so we're not going to verify our results, we're just doing it. So 33 is y equals the sine of x, y equals 0, x equals 0, x equals pi. So these are the two vertical lines. This is the x-axis. This is the function. So let's just plot it. So I'm going to change over to my graphing program. So we're going to put in the function is sine of x. We're going to go from 0 to pi. And x, let's see, y is going to go between 0, -1, +1. So we'll put -1, +1, and then we'll push graph. So there it is. So this is the function, and we're going to go ahead and copy that into the thing so we can draw some stuff. Okay, so let's go back to the smartboard stuff. And we get rid of the little camera. Okay, so there's the function, sine of x. That's the red curve. And then we have two other situations. So we have x equals 0, which is this point, and x equals pi, which is that. So really, there's no vertical lines, just a top line, a bottom line. So this is the area we're talking about. And we're going to rotate that around the x-axis. So it'll make kind of a football-shaped thing, kind of a weird-shaped football, probably more like a rugby ball. So this thing will rotate around, and it's symmetric. So theoretically, we could do half of it and multiply it by 2, but we don't need to. So again, because it's if we draw a rectangle, let's draw a rectangle to show what we'd revolve around the x-axis. It would be something like that. So that's my rectangle. The top of the rectangle is the sine of x, and the bottom is 0. So again, the volume of using the this method around the x-axis is pi times the integral from a to b of the quantity r of x squared dx. And r of x in this case is equal to the sine of x. Okay, so and what is a and b? A is equal to 0, b is equal to pi. So we plug that in, so we get volume is equal to pi times the integral from 0 to pi of the sine of x, quantity squared dx. Well, we know the integral of the sine is going to be the cosine, but negative the cosine, but the problem is we have this squared thing. So if we use u substitution, said u is this, we'd get u squared, but d would be a cosine. We don't have the cosine there, so that doesn't work. So a lot of times in cases like this, you have to use trig identity, and apparently my book is missing that particular trig identity, so I'm going to get my newer book. But if you go to the front of your book, there should be that kind of cardboardy page. And if you go to the trigonometry section, you'll see that there are power reducing formulas. And the particular one I'm looking at, I'm going to write it verbatim, is sine, says the sine squared of u, which is the same as the sine of u quantity squared, is 1 minus the cosine of 2u divided by 2. So that's trig identity, which is good for all values. So I'm going to make that substitution into my equation. So you get the volume is equal to pi times the integral from 0 to pi of 1 minus the cosine of 2x divided by 2, whole thing times dx. So let's factor out the 2 just to make it easier to deal with. So I get 1 minus cosine of 2x dx. And so we can do these separately because they're just connected by a negative sign. So the first part's easy. The second part, you've got to remember we've got 2x. So we're going to, let's just do that. So let me break it up into two parts so that nobody gets confused. So we get 2 pi over 2 times the integral from 0 to pi of dx. 1 times dx is dx. And then we've got the second part, which we subtract the integral from 0 to pi of the cosine of 2x dx. And there we go. Close the bracket. Well, the integral of dx is just x. But let's do the second part first. Actually, what I'm going to do is I'm going to add a page, and then we'll come plug it back in. So what is the integral from 0 to pi of the cosine of 2x dx? Well, let's let u equal 2x, because I know what the integral of cosine is. It's the sine. So if I can make that substitution, I get u is 2x, so du is equal to 2 dx, or dx is equal to du divided by 2. So I can make the substitutions. And also, because it's a definite integral, let me go ahead and change the limits. So when x equals 0, u equals 2 times 0, which is 0. And when x is equal to pi, u is equal to 2 times pi, which is 2 pi. So we make this substitution. We get the integral from 0 to 2 pi of the cosine of u du. And that's u equals 0 to u equals 2 pi. And I'm trying to decide whether to plug that back in now. Yeah, let's go ahead and do that. Okay, so the volume is equal to pi over 2 times the integral from 0 to pi. So let me just put that in there. Okay, 0 to pi of dx minus the integral from 0 to 2 pi of the cosine of u du. Oh, I forgot a half, didn't I? Yeah, I got a, that's divided by 2. Okay. So we actually get a divided by 2 right there. Okay. So now we're going to finish it up. So the volume is equal to pi over 2. The integral of x dx is x. So we evaluate that between 0 and pi. The second part, the integral of the cosine, so we get, well, first we get 1/2 from this thing. So we get 1/2 times. The integral of the cosine is the sine of u, evaluated between u equals 0 and 2 pi. So let's go ahead and evaluate the limits. We have pi over 2 times, okay, so plug the upper limit in, pi, subtract the lower limit, which is 0. So it's pi minus 0. Then we have negative 1/2, the sine of 2 pi minus the sine of 0. But the sine of 0 is 0, and the sine of 2 pi is 0. If you don't believe me, stick it in your calculator. So this whole thing goes to 0. You have 0 minus 0, which is 0. So all we have left is pi here. So the final answer is going to be pi times pi, which is pi squared, divided by 2. And this is problem 33, and the answer is pi squared over 2. So that's correct. Okay, this is problem 35, section 2, chapter 7. So it says find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the x-axis. Verify your results using the integration capabilities of a graphing utility, which we're not going to do. We're just going to do the first part. So you get y is equal to e to the x minus 1, y equals 0, x equals 1, x equals 2. And so we can graph this, and I'm going to have to start up the graphing program. So bear with me here while I get that going. It won't take me too long. So hopefully you're seeing this on the page. I'm pretty sure you are. So the graph I'm going to graph is e to the x minus 1. So we're going to do ext, which is exponential. And I think I'll do that. Okay, e to the x minus 1. So it's going to be the e to the x translated 1 unit in the x direction, positive x direction. So that's what we get. So this is e to the x usually goes through x equals 1, y equals 1 at x equals 0. So now it's going through it at x equals 1. So that is the curve. So let's so hold on just a second. Screen went blank. I'm going to get my camera so that I can copy this thing over. Okay, so that's the graph, and now it will be hopefully in the smartboard file that we just did. Okay, so there's a graph, and now I can draw some stuff on it. So the red curve is y is equal to e to the x minus 1. And so the other limits are going to be y equals 0, which is this horizontal line. And we have x equals 1, which is that, and we have x equals 2, which is that. So it's going to be this area right in here. And they're asking us to rotate around the x-axis. So this is just going to be using the disk method, not the washer method, because since the bottom of the curve is equal to the x-axis, we're just going to have this as the upper curve. So we know that the volume of a solid rotated around the x-axis using the disk method is pi times the integral from a to b of capital R of x quantity squared times dx. So this is R of x, is the upper curve. The inside curve is just equal to the x-axis. So we know that R of x is just equal to e to the x minus 1. And the limits of integration are going to be from x equals 1 to x equals 2. So the volume is equal to pi times the integral from 1 to 2 of e to the x minus 1 quantity squared dx. So let's multiply out. That's usually what we do, is we square the term that we have. So when you square this, that means you're going to multiply each term by 2. So you get e to the 2x minus 2 dx. So we're going to have to use a u substitution here to make sure that we keep everything straight. So we're going to let u equal the exponent, which is 2x minus 2. Therefore, du is going to be just 2 dx. Derivative of that is 0. The derivative of 2x is 2, and we add the dx term. So you can see what we're going to need to do here. I'm going to just do it up here. Is I'm going to multiply by 2 here, and I'm going to divide by 2 there. And therefore I have 2 dx will be du, and I have 2x minus 2, which would be u. So we can rewrite the integral as pi over 2, the integral from 1 to 2. Now, I'm going to do the substitution back in. In some ways I could change the limits of integration, but let me just do it the other way. So we're going to have e to the u du. So that's u, this 2 dx is du. Okay, so we integrate it. Pi over 2, the integral of e to the u is e to the u. And our limits are x. So let's go ahead and change back to x. So we're going to have pi over 2 times e. U is equal to 2x minus 2, so we get 2x minus 2, and we evaluate that between x equals 1 and x equals 2. And finally we plug the numbers in. So what we have is pi over 2 times e, and we plug in 2 in for x, so we're going to have 2 times 2 minus 2. And our lower limit, we subtracted, so we're going to have 2 times 1 minus 2. And so we have pi over 2 times e. We've got 4 minus 2 is 2, so we get e squared minus, and we have e to the 0. E to the 0 is 1. So we end up with pi over 2 times e squared minus 1. And you could leave it as that, but let's just calculate it because we know what e is. E is in our calculator. So let's come up with a decimal number for this area. So we'll have to take pi divided by 2 times the quantity e to the second power minus 1. And I get 10.04. So that's the volume of this function, e to the x minus 1, rotate around the x-axis between x equals 1 and x equals 2. So I've checked the solution manual, and that is correct solution. They show both this and that, the two options. So let's, for you guys who want to review, let me just go back through here. So here was the four terms that defined the area. Y equals e to the x minus 1, which is this red curve. Y equals 0, which is this horizontal line at y equals 0. Vertical lines at x equals 1 and x equals 2. So this is going to be rotated around the x-axis. There's no inner radius because we're rotating around the x-axis, and the inner surface is the x-axis. Now if they had said something like y equals 1 or y equals a half, then you would have to use the washer method, but in this case we don't. So the volume for a solid rotated around the x-axis using the disk method is pi times the integral from a to b of the upper curve, the curve defining the outside of the volume, squared times dx. And this is our curve, e to the x minus 1. So we just plug it in. The limits of integration are from x equals 1 to x equals 2. And so we multiply this out to get e to the 2x minus 2. We say that's u. We take du, we get 2 dx. We have dx, but we didn't have the 2, so we multiply by 2 here, divide by 2 to balance it out. And we can rewrite it in terms of u. pi over 2, the integral from 1 to 2 of e to the u du. And actually, we substituted back in, but let's, as a intermediate step, I'm going to add another page. And if we wanted to redefine the limits, so when x equals 1, u is equal to 2 times 1 minus 2, so u is equal to 0. So that would be our lower limit. And if you go to x equals 2, u is equal to 2 times 2 minus 2, which is u is equal to 2. So we could rewrite that as pi over 2. The integral from u goes from 0 to 2 of e to the u du. So you get pi over 2, the quantity e to the u, evaluated between u equals 0 and u equals 2. We don't have to plug it back in. And in that case, we'd have pi over 2 times e squared minus e to the 0, which is pi over 2 times e squared minus 1. So we could do it that way, or what we did previously is we substituted back in for u in terms of x and kept the x limits of integration. So then we plugged it back in and you get the same answer either way. Problem 48. So the idea here is we are supposed to use the disk method to verify that the volume of the right circular cone is 1/3 pi r squared h, where r is the radius of the base and h is the height. So let's just draw this. Here's our coordinate system. And if we were to take a line here and draw it like this, and then we took a vertical line to represent this. If I take this area and I rotate it around the x-axis like that, it will create a cone. This dimension is h, the height of the cone, and this is the radius of the cone. So this line is y is equal to, well, the dependent variable is x, so it's going to be x. What is it going to be? Well, let's think about this. When x equals r, y equals h. And when x equals 0, y equals 0. So if you were to, these are 2 points, so you could use a point and the slope. So the slope is equal to the rise over the run, which is going to be r over h. So that's the slope. And if we were to use the point slope form of the linear equation, it's y is equal to y minus y1 is equal to m times x minus x1. In this case, one of the points is 0, 0, so that goes there, and so you get y is equal to the slope, which is r over h times x. So when x is equal to h, y is equal to r. Okay, so that works out right. So that's the equation. Y is equal to r over h times x. So if we draw our rectangle, just to show what we're doing, we're drawing up a rectangle that's some x value, and we rotate that around the x-axis, and then we sum them all up. So we use the disk method, and the disk method would say the volume is pi times the integral from a to b of r of x, quantity squared dx. In this case, r of x is equal to r over h times x. So we plug that in, and you get volume is equal to interval from 0, so it's here, to h of r over h times x dx, this thing squared dx. So that becomes pi, the integral from 0 to h of r squared h squared x squared dx. Well, r and h are constants for a given right circular cone, So we can bring those out. So we'll have pi r squared over h squared times the integral from 0 to h of x squared dx. And so the integral of x squared dx is x cubed over 3. So we get our constant, which is out front. We get x cubed over 3 evaluated between the two limits, which are 0 and h. So we get pi r squared over h squared times h cubed over 3 minus 0 cubed over 3. Of course, that's 0. So, and then we can simplify this by, we have h squared and h cubed, so that leaves us h in the numerator. And we have 1/3, so we'll get pi over 3 r squared h, which is the answer that we're looking for. So that's how it works. Last problem in this section is 53. And what we have, 53, we have this shape, y is equal to 1/8 x squared times the square root of 2 minus x. And you can see it in the book. And again, it's rotated around the x-axis, and the center is the x-axis. So we can use the disk method, which will say the volume is equal to pi times the integral from a to b of r of x, which is what we have up there, times dx. And our a is equal to 0, which is the origin, and b, which is equal to 2. If you look at the x-axis on page 464, you'll see that it starts at 0 and ends at 2. So all we have to do is plug it in. Pi, integral from 0 to 2 of the quantity 1/8 x squared square root of 2 minus x quantity squared dx. So how does this thing work? Well, you square everything inside, so you get v is equal to pi, and from 0 to 2, you get 1/64 times x to the 4th times 2 minus x. So when you square the square root, you just get what's inside, so you get 2 minus x. Whole thing times dx. And then we just multiply, we'll factor out the 64, so we'll get pi over 64, the integral from 0 to 2 of x to the 4th times 2 is 2x to the 4th, and then you'll get minus x to the 5th. X to the 4th times x is x to the 5th. So it's just a simple polynomial. So when we integrate this, the constant stays out there. We end up with 2 times x to the 5th divided by 5 minus x to the 6th divided by 6. And we evaluate that between 0 and 2. And of course, when you stick 0 into a polynomial, you get 0. So all we have to do is plug 2 in there. So we get v is equal to pi over 64 times 2 times 2 to the 5th over 5 minus 2 to the 6th over 6. Well, it turns out 2 times 2 to the 5th is the same as 2 to the 6th. So what is 2 to the 6th? So you got 2 times 2 times 2 is 8. And if you square that, you'll get 2 to the cube squared is, so we get 8 squared, which is 64. So we'll get pi over 64 times 64 fifths minus 64 sixths. You can see we just cancel the 64 out because we've got the denominator in both numerators. So we get v is equal to pi times 1/5 minus 1/6. And a quick way of doing this is you cross multiply. So you get 6. 1 times 6 is 6 minus 5, which is 1 times 5. And then you divide by the product of the two, which is 30. So we'll get 1/30th. 1/30th times pi is pi over 30 as the volume, if I did everything right. So let's look and see what it is. Pi over 30, correct.